Okay, so we're going to do phase diagrams today. We've been doing phase diagrams, PV diagrams, but we really haven't seen many phase changes. We've just been looking at PV plots of gases. Then we last time looked at this condensation region. Yes? Oh, okay, yes, very good. I plugged it in. I thought it could be. And so we looked at the gas regions for pressure versus volume. Today we're going to get into pressure versus temperature. So PT phase diagrams. And then we'll look at all three together. So this is, in the past I had changed books to Engel because they had a three-dimensional phase diagram and I had never seen that before. And so that really lit me up because then I saw how PV and PT diagrams were related. So that's in today's notes. And I've got a little show and tell thing that we can pass around. So we're going to connect, we're going to look at PT phase diagrams, we're going to talk about the phase rule, and then we're going to connect the PT and PV phase diagrams in a three-dimensional shape. And then we'll take a Kahoot. So this is the pressure-volume relationship for a substance. Now this would be for a single substance, a pure substance. This is a generic one. There, those lines don't really have numbers on them, so we don't know what substance this is. But for a particular substance, you would have a particular critical point. That'd probably be the easiest thing to identify on this phase diagram would be the pressure and the volume for that critical point. We wouldn't know the temperature because it's not shown on this diagram. Okay, but we would have the pressure and the volume, critical pressure and the critical volume, and that would be up there at the critical point. Last time we looked at just the gas and liquid. So we looked at isotherms that came along like this. And then there was condensation. And in this region you had liquid and gas in equilibrium. And then at this point it went up in the liquid. And it, a small change in volume gave a really steep change in pressure. But then eventually if you press on it long enough, you'll get it to freeze. And so then you hit this and it cuts across, and then you have solid and liquid in equilibrium. And then once you've pressed that down, then you're pressing just on the solid. And it's really steep here. And that's the pressure-volume relationship of a solid. Very incompressible, meaning it takes an enormous amount of pressure to change the volume of the solid. But yet solids do have a measurable compressibility. And how would we measure those things? Well, we put them in, high-powered presses or even diamond anvils. So this is a geared arrangement with the pressure points being diamonds. This is one of the hardest materials. And so we can use that diamond to press on other things that are less hard than diamond, and we can measure their compressibility. And we can actually shoot lasers through the diamonds and do spectroscopy, and that's how we kind of get information on these different phases, by doing spectroscopy at enormous pressures. So millions of atmospheres in these diamond anvil cells. And they're really tiny and they're not that expensive. It's amazing that you can get millions of atmospheres of pressure in something that you could hold in your hand, and do spectroscopy through the little diamond windows. It's pretty cool. And so you should be able to narrate what happens with any stripe through these PV diagrams. That's the skill I'm trying to teach in this middle part of the course. Is for you to I drop a phase diagram in your lap and I point to a spot and you tell me what's going on there. So if I dropped a point right here, you could tell me what was that point. Is it solid, liquid, or gas? Solid. But if you didn't have those labels, could you do it? Okay, so that's the thing that you need to practice on, is taking all of these phase diagrams from the notes and erasing or obliterating the labels, and passing them to each other, saying, okay, tell me where, this point is. So if we go from this point over here and we hit that line, immediately we have sublimation. So in this region we have solid and gas in equilibrium with each other. And so this right here is the volume of the gas at that temperature. And this is the volume of the solid at that temperature. And somewhere in between, let's say we're in a container right here. It's like there's a fulcrum on that line that goes across, and that would tell you how many moles you have in that system that are solid and how many moles you have in that system that are gas. So if you were to balance this seesaw, you'd need a pretty big kid over here, right? Holding on, that's a little kid. And you have a tiny little kid over here like a child for that to balance. So you have much more solid, if that was your container volume, you'd have more solid than you would have gas. And so you can use that idea of a seesaw, a tie line, seesaw, to determine which is dominant at that volume. If you were way over here, if the volume of the container were way over here and it was at equilibrium, we'd have an enormous amount of gas and just very little solid. Again, to get that line to balance, which one's going to be most abundant? So that's another question you can answer using these phase diagrams.
So whichever side is closer to you, that's the one that's more.
Yes, and so just think of a seesaw, or a board, a plank on a log, and you're trying to get that to balance. You got to put the heavier person on the shortest piece and the lighter person on the longer piece. Yes.
You just want us to know, like, general, which is heavier?
Yes, and then later, like in another 2 lectures or whatever, we'll have an example where you will calculate it in the 2-phase mixture. But at this point, I'm just talking about in general terms. Same thing happens up here with the liquid-gas equilibrium line. If this right here is the fulcrum, then we have a lot of gas and very little liquid. If we're right here. Okay.
On the brown strip that says solid and liquid,
Yes.
if it's going all the way straight up, does that mean temperature doesn't matter in that little pressure and volume range?
Temperature, because it's coming out of the board, is difficult to see. So that thing is not straight up, it's tilted in temperature. Okay? And it can be tilted towards higher temperature or tilted towards lower temperature. So we'll see that for water. And that's why this 3D object that I've got is really awesome.
Okay, so is this like the ones from CHEM, except like, so it was like curved like this in CHEM, and there was like, oh my god.
Yeah, so you've got it. It just
like,
clicked for you.
Okay.
That face, this face right here, this big face right here, when you're in a PT diagram, you're looking at it from the side, and the whole thing is curved.
Okay.
Yeah. So here's a PT diagram. And so this face right here, this orange-looking face right here, is going to flip sideways and is this line right there. Okay. And this brown solid liquid panel, okay, is going to flip sideways, and it's this right here. This right here. And then the sublimation line, this one, this down here, this kind of gray, blue, is going to flip sideways and be this place right here. So we've taken the phase PV diagram and rotated it, and now we're looking at it along the temperature axis, and we see these things. And so you can see the critical point up there at the top. You also see why if you take 1 atmosphere and you take a solid at 1 atmosphere and you warm it up. So you've got ice, it's at 1 atmosphere, it's a solid. You start warming it up. It hits here and the temperature stops until it all melts. And so at here you don't see anything going on. But over here, you're moving across this volume from the volume of the ice to the volume of the water. But it's all at the same temperature. Okay, that's right here. And then you start raising the temperature of the liquid, and that's when you're moving across this region. So the volume of the liquid's changing slightly as you raise the temperature, but then you hit the point where it starts to melt. It starts to boil. And so we've raised the temperature of the liquid, now we're at the boiling point, and we sit at that boiling point until all the liquid is turned to gas. That's moving across this region here, liquid gas. And then you have all of the water now steam, and here we're just heating the steam. And the volume's changing dramatically because we're at 1 atmosphere and we're heating steam. It's wanting to expand, and it is expanding, but we're still staying at the same pressure. So it's an isobar. And so this is an isobar across here. And you see that once you get to gas, it's going to expand as you heat up that gas. And you can still stay at 1 atmosphere pressure if you keep increasing the volume. So you have a flexible container. So that's relating the 2 phase diagrams together. Let's look at this PT diagram. So anytime you get a phase diagram or any plot whatsoever, go to the axes first. What's the y-axis? What's the x-axis? This is basic. You've got to know what's being plotted, and that's where your probably your first mistake would be if you don't know if it's a pressure temperature, pressure volume phase diagram. Later, when we get to two components, the x-axis is going to be mole fraction, like component A in component A plus B, right? A mole fraction, just a binary mixture. And the y-axis could be pressure, the y-axis could be temperature. So you've got to know what that y-axis is. So you got to pay attention to your axes. It's critical. And this triple point here is just a three phases in equilibrium. You have solid, liquid, and gas in equilibrium at that triple point. On the PV plot, that's this line right there. So you've got solid in equilibrium with liquid and equilibrium with gas. And so you've got three substances in there. You've got solid, which has this molar volume, liquid has that molar volume, and gas has that molar volume. So if I dropped you anywhere in any of these phase diagrams, you should be able to tell me what phase you're in. If you hit a line, you should be able to tell me what's going on at that line. Is it an equilibrium line? And so on. Then this also, 1 atmosphere is what defines the normal melting and normal boiling points. So that's a vocabulary word for you. Normal boiling point is at 1 atmosphere, even though standard ambient temperature and pressure is 1 bar. So it's all screwed up. I didn't do it. Okay. Yes.
Will this look different for various molecules?
Yeah. One critical difference is that water has this positive slope to the solid liquid line, so that if you press on the liquid, it'll no, I got it backwards. Water has a negative slope to this. Let's go find water. There's water. Okay, look at that solid liquid line. It has a negative slope. It leans to the left.
Okay.
And that's unique for water. There may be a few other substances in nature, but 99.999% of all substances have a positive slope to that line. It leans forward because the solid's more dense than the liquid. But water, the liquid's more dense than the solid. So if I press on the solid, it can melt. I press on the solid ice and it can melt. So I'm putting it in a smaller space and it becomes a liquid. Most other things, the more dense material is the solid.
I guess disregarding the slopes or positive, negative, will all the phase diagrams have a general same look?
No, they get kind of crazy. Yeah.
Oh, okay.
And so we'll look at some experimental ones here in a second. So if I walked you through this path A, we go from solid, then we melt, then we go through liquid, and then we boil, and then we have the gas. We're just heating that up. If I go lower, then we have a solid, and then it sublimes. And so it sits at this sublimation temperature until all of the solid is gone and it becomes a gas. And then you can warm up the gas. Now these are in equilibrium situations, so you would have it in a container to where this was happening slowly. The solid was turning into a gas. And slowly it's in equilibrium. And what does equilibrium mean? Well, it means that, if you're sitting at equilibrium and you're not trying to change the temperature, you're not putting heat in or pulling heat out, then just as much solid is turning to gas as gas is turning to solid. So that's equilibrium. The forward and the backward rates of reaction are the same at equilibrium. And so if I sat there at that temperature, you'd have solid going to gas and gas going back to solid. Most of that's going to be back on the solid, but you'd have some going to the walls of the container. And so just like in your freezer, that ice will sublime and move around and then deposit elsewhere. So you can have an equilibrium situation at a constant temperature where the solid moves around. How does this happen? Well, it's sublimation and redeposition. And that's what's happening at equilibrium.
Is it possible to make ice without air pockets?
Yes, when you make something like that, very slowly, you have what's called a single crystal. And so you can grow a single crystal of a solid substance. And so you could probably grow single crystals of ice. I don't know of any examples, but...
Would it have to be in the liquid or?
A lot of times they grow them very slowly and they draw them out of the liquid. And so that there's a lot of time for the liquid molecules to find their perfect orientation. because in a crystal, there's an energetic reason for that molecule to be in exactly the orientation that it's in. And so you've got to have time for them to sample all the possible positions, and then when they fall into that hole, energetically, they're stuck. And so then you just build up these layers one at a time, and if you draw this out slowly, that's how you make single crystals. So I bet you could make a pretty good single crystal of ice, because it's so energetically favorable to form those hydrogen bonds. Yeah, they make single crystals out of silicon. That's what these silicon wafers for years, I don't know if they're still using single crystal silicon, but they would draw these huge 20 centimeter boluses of silicon out of molten silicon and then slice them really thin. That's what our substrate was for our circuit boards. I mean, for our integrated circuits. Is a single crystal silicon drawn out of this crucible. Now, how do you keep it hot? You put it in I think it's iridium, I'm sure, but you make a crystal that you can heat with an inductance coil. So you just have a radio frequency coil around this crucible, and you're just pumping electricity, AC, into this coil, and it heats up that crucible and melts the metal inside for the substance. And so you can make these, again, trying to play with this equilibrium between liquid and solid, you can give that solid a very slow time to form and make really perfect crystals. Let's see. I'm not sure what I'm trying to do with C, except just that I'm following equilibrium all the way up. So if you let pressure and temperature change together, you can follow that phase line all the way up. D, if I'm starting up here, I guess I'm just telling you a different pass through here. If I start up here, I'm in the solid. I start to release the pressure, and it becomes a liquid right here. It would sit there until all the liquid is formed, and then I'd be reducing the pressure. And then here, it would sit until all the liquid turns to gas. So I guess that'd be like pulling a vacuum on it and drawing the pressure down. So let's think about the degrees of freedom. If we look at the phases, say we're staring at this and we say, okay, I've got a single phase. How many degrees of freedom do I have in my variables? Well, I can change the pressure, I can change the temperature, and it still stays one phase. It's ice, say. But if I've got liquid and solid in equilibrium, so it's melting, and I have, say, half liquid, half solid, I could see the two phases in there. What are my degrees of freedom? Well, if I change the temperature and I want to maintain two phases, the pressure has to change. And so I've lost the degree of freedom if I want to maintain two phases. What I mean is this line right here, this phase line, tells me if I change the temperature, then the pressure follows. If I change the pressure, the temperature follows, if I want to maintain two phases. So right here, because I have two phases, I've lost the degree of freedom. F is degree of freedom. Now, if I just go back to one phase in the liquid, I have 2 degrees of freedom. I can change the pressure and the temperature, independently. I can move in any direction in 2 dimensions and still maintain one phase. But if I want to keep 2 phases in equilibrium, I lose a degree of freedom. Now, that very simple observation is what allows us to come up with the phase rule. This is just what I said, in text. That this analysis of degrees of freedom in the phases comes up with the phase rule. So this is the phase rule. And what I talked to you just now about was just a single substance, water. If you have multiple components, you get more degrees of freedom. And so you can have multiple phases in equilibrium with each other with more components and still maintain degrees of freedom in terms of being able to change the temperature and pressure. And this is something that Gibbs derived, so using the Gibbs energy. And this really, the rule, we don't use it very much, but I'll tell you what it does do for us on the next slide. So whenever you're ready, you can look up and I'll switch. And the bottom line is this phase rule allows us to determine these intersection points. Because what if we have 3 phases in equilibrium? Looking at the phase rule, we have one component, and we have 3 phases in equilibrium. We've lost our degrees of freedom, right? So you have one component, 3 phases, so that's minus 2 plus 2. And so we have 0 degrees of freedom. And what that means is that a triple point, 3 phases in equilibrium, is a defined pressure-temperature pair. And you can't change the temperature or the pressure, or you lose one of those phases. It goes to a 2-phase region, or maybe it goes to a single-phase region. And so you really don't have any degree of freedom to change a triple point. That's a defined spot on these phase diagrams, a triple point. The intersection of 3 phases for a single substance, you have no choice. It's going to be a PT point on that phase diagram. And so what the phase rule can tell us then, for a single component, you can't have 4 phases in equilibrium. So this quadruple point here is forbidden. And so if you were to collect data on this, let's say you measured these different data points, pressure, temperature, regions, and this was coming down, these were moving up, and this was moving over, and this was coming down, and it looks like all of these are going to converge on a single point. You know from the phase rule, you're not going to have a quadruple point for a single component. And so what you need to look is very close to that point, and you'll see probably something like this. This one will curve around and hit right there. And so you have a triple point here and a triple point there, but you would not have a quadruple point. And so you know that one of these lines diverges. So probably, say this one. If you collect the data, you'll see that, it converges and hits this boundary. Or it moves over and hits that boundary. Or this one skips that point and comes over here and makes a triple point. So it just helps us sort out these phase diagrams. And that's really all I'm showing you with the phase rule, is that it shows that quadruple points are not allowed for a single substance. Now, if I have 2 components, yes, you can have a quadruple point. You can have 4 phases in equilibrium with 2 components. So let's look at some experimental phase diagrams. So this is water. And again, when you're dealing with real data, this is kind of hard to show sometimes because of the regions. They're either squished down in the bottom regime or they're too big. So this plot is an experimental diagram for water, and it's broken in the middle to change the Y scale so we can get it all on one slide. So that's what that gray bar is. It goes from up to 2 atmospheres, and then there's a break, and then it goes by thousands, 2,000, 4, 6, and 8,000. So this is the change in scale. So we have the triple point, and for water that would be defined as 0.006 atmospheres and 273.16 Kelvin. The normal melting point and boiling point at 1 atmosphere is 273.15 and 373.15. You've seen those before. That's 0 and 100 degrees Celsius. So you have steam over here. So this is the PT diagram you're used to seeing. But notice at 2 atmospheres, we don't have quite the critical point for water. But when we change the scale, the slope of this line comes really shallow. And so way over here, then we have the critical point for water. The critical temperature is 647.30 Kelvin. And I can't remember the critical pressure, let's say. But then look what happens with the solid line. So this ice is given the name ice 1. And it has a triple point with ice 3 and liquid. And it also has a triple point with ice 2 and 3. And so if you think about ice's structure, it's kind of like the diamond structure. Every oxygen has tetrahedral bonds coming off of it, and those are hydrogens. 2 of those hydrogens are covalent bonds. The other 2 hydrogens are hydrogen bonds from 2 other water molecules. And in fact, it's very expanded. That's why solid ice is less dense than water. So in order to make all these hydrogen bonds, it has to expand a little bit. And it floats because it's less dense than water. Now, the other solids that you're familiar with, like if you have molten brass and it starts to solidify, where's it going to solidify? It's going to be in the bottom and you won't see it. But if water starts to freeze, it's in the top. This is one of the coincidences of nature. If water didn't have this behavior and expanding upon freezing, we wouldn't be here. Because all of our food is grown on soil, and all the soil came from rocks that weathered because ice expands when it freezes. It breaks apart those rocks, it gets in the nooks and crannies and keeps splitting things apart, and that's where the soil came from. So it's amazing that we have this property of ice expanding upon freezing. But these other phases, that's crazy if you think about it. But if you put that expanded form of solid ice and press on it, some of those hydrogen bonds collapse. And so then the water molecules get closer together. And it's it's not stable at 1 atmosphere, but at that high pressure, that's the stable form. And so you'll get a phase transition. And it'll change, and you'll have that pause until all of the ice moves around and grows into this new form, and then you can move into that structure. So if we're raising the pressure here at this temperature, we would pause at that line until the energetics, convert all of ice 1 over to ice 3, and then we can move and increase the pressure on ice 3. And then we go up to ice 5, and then we come up here to ice 6, and there's 7, 8, 9. I think it's gone up to 12 now. 12 different phases of ice.
Where's ice 4?
Yeah.
Is that under 200?
And so I looked at that this morning just to Google it, see if I could find any information on it. And they say it's metastable, that it's not stable enough. It will revert into ice 3 or ice 5 or ice 2. So the thing with the chemical literature, like the 0th law of thermodynamics, they publish literature on ice 4, and then they try to characterize it more, and they're like, it doesn't have an independent place on the phase diagram, so don't put it on there, And so when you form ice 4, it's not stable. It will convert over to one of the other
So is
3
ice
forms.
4 like the triple point between 2, 3, and 5?
I haven't found out where it's located on here, and we could probably go back to the literature and actually find the papers. But this morning's search, I've searched for it every once in a while. This morning I searched again. I found this site here. I don't have Java loaded on my computer because right here you've got these little JMOL. Let's see, where's the thing? But see, it talks about ice 12, ice 3, ice 5, ice 6, But here's the structure of ice 4. It says it forms a rhombohedral crystal. I've got the crystal dimensions on it here too. It talks about it being metastable. Here's the phase diagram. Let's look at that. There we go. Look at that. Let me kind of make it bigger if I can. Does that help? Yeah. Okay, so here's...
15.
Yeah, so...
And then you paid a 15.
Yeah, then it gets real dense in here around ice 2 and 3. Here's 5. Here's 6. And so we've got 15, beta 15, I don't know, 7, 10. But what's interesting about this is you've got solid ice above 373 Kelvin. Wait a minute. It says solid ice that's hotter than boiling water. So it's just kind of to blow your mind a little bit about these phase diagrams. Yeah, so nature gets pretty crazy when you get into these extremes of pressure and temperature.
I think what's most impressive is how they would have measured and found the crystal dimensions of such things, because it's so hard to picture. When you have crystal structures on that level.
Yeah, I don't know how they did that. I mean, maybe they shot X-rays through a diamond anvil, but think about the confusing data that you would get. You get all the electron diffraction or X-ray diffraction from the diamond, which is pretty easy to pick out because it's so regular.
But then you have so many different phases and different crystal structures overlap.
Yeah, I know. So I don't know how they did it. So props to them.
It's impressive.
Yeah, it's very impressive.
Do the different water types look different, visibly? Would they just be easier to see through, or?
That's a good question. I don't know.
I don't think you would be able to know that. There's no way they did this on a large scale. It's all small.
But you would be able to see with do spectroscopy on it. So you might be able to see. I mean, maybe some of them. If you get the atoms close enough, that then the atomic orbitals, it starts to act like a network solid, to where you might have bond delocalization. I mean, you could see color develop. I don't know if these are colored, but if you get the HOMO-LUMO gap through pressure and extended electron clouds, close enough to where you have something in the visible, then you could have colored substances. Like it would change color. So I don't know if that happens in ice, but
so would that be like part of like the Arctic and like far up north where
and some
ice is
planets
blue?
like these the whatever Europa, I think it's an ice planet around a moon of Jupiter. I don't know what kind of pressure regime it has. They dropped this probe into Jupiter to measure the pressure that went down, but I don't know what kind of pressures they reached. But there's a lot of fun stuff that you could look at in terms of these phase diagrams. You get into a different region where things like H2S, which is a gas at our 1 atmosphere pressure, might be liquid H2S. Definitely not hospitable for life, But like Io is just a crazy lava planet or moon. It's a moon of Jupiter. It's so close to Jupiter that the gravitational forces on the front and the back half of that planet, as it rotates, are just grinding the planet, and it's melting it all to bits. Yeah. Yeah. So it's in such a gravitational curve that the gravity on one side of the planet is substantially different than the other side. And so as that rotates, you can imagine just the grinding in the rocks due to the gravity. And the first probe that so Io's moving around, and they saw this bulge on it. And they're like, what is this bulge on the planet? So you think about looking at a planet in its horizon, and you see a bulge. That's a big bulge, right? Because you get the whole planet in view, or moon in view, and then you see this bulge come around. And as they got closer, they realized it wasn't a bulge, it was the plume of a volcano. That was like planetary scale volcano on Io, that you could see when you had the whole planet in view. You could see the bulge from the plume of this volcano. That's an impressive video. You should definitely probably be able to see that if you Google it. When I saw it, my mouth dropped open. That was pretty cool. So here's CO2. Again, down here at 1 atmosphere, we know, because we like to play with dry ice, it sublimes. And so you just set it on the countertop. It's not at equilibrium, but it is subliming, trying to reach equilibrium. So it's just spitting out CO2 gas. Okay. It also doesn't melt when you put pressure on it. So I don't advise this because something could happen, but just to show that it wouldn't be slippery if I stepped on it, I put dry ice on the tile here and I stepped on it. And it didn't budge. If you do that with ice, of course it's going to be melting and lubricating its motion on the floor, and don't step on a block of ice because it's going to shoot out from under you. But CO2 sitting there subliming, when you step on it and it doesn't budge, it's kind of cool. Not that proves anything. But. Then we have the triple point of CO2. I had a professor, Glenn Evans, in grad school. I shouldn't call his name out. But, he was a theoretical chemist, totally pencil and paper. That was his research. He'd sit in a coffee shop and just derive equations. And I was TA for him in Gen Chem one time. And he was going to show the triple point of CO2. So he had the machine shop make up this Lexan tube, and he put CO2 in there, and he put these plugs in the bottom, and it started building pressure. You got to get to 5 atmospheres, right? And he thought that this Lexan tube was thick enough that it could handle it, and it started cracking because of the cold. So the cold of the CO2 started to crack that polymer, and so cracks were developing, and he was like, everybody out, so all the freshmen had to grab their books real quick and leave the classroom because he basically had a pipe bomb up front. So that I didn't get to see it because everybody had to run. So I'm not going to try that. But every time I see the triple point of CO2, I'm reminded of that classroom. It was great. It didn't blow up, but it did crack and leak. Okay. So then we have the break in the y-axis scale, and they have the critical point for CO2, 304 Kelvin, so even lower than water. Water was 647 Kelvin, and 72 atmospheres. I didn't get that pressure for the water critical point. We can have it on that table in the previous set of notes. But these are not that extreme temperature and pressure regime. And so it's fairly easy to make supercritical CO2. And in fact, now they have separation techniques like supercritical CO2 chromatography. So it's not really gas chromatography or liquid chromatography, because it's kind of like a gas chromatography in that it's a gas flowing through there, but it has the density of a liquid. So it's a different kind of chromatography. It's a bit expensive because of the pumps and the stainless steel tubing, because you got to hold the 72 atmospheres. You can't use glass capillaries. But it separates things faster than the other two techniques in certain situations. So you run across supercritical CO2 chromatography, and now you know it's not that hard to do. 72 atmospheres is not that hard to achieve, and certainly stainless steel can handle it. Okay. This one is weird. This is helium. So again, we have triple points, we have critical points, and so on. Yeah, but look at the pressure and temperature region. 2 Kelvin, 5 Kelvin, 0.1 bar, 0.01 bar. So, but it's, again, phase diagram. You see, if I dropped you anywhere in here, you should be able to tell me something about it. Now, helium also has a couple of different solid phases. It has HCP and BCC. What do you think those are? They're not Roman numerals like water.
Critical point.
No, the critical point's over here, but that's
Is it not a solid under 10 pressure?
both of the, yeah, that's right. Under 10, you don't have any solid helium.
That's crazy.
Yeah, it is kind of weird.
Yeah.
So up here, the solid line stops. They just stops here because they don't have any data for that, so they just didn't draw it. So they have data for this region: solid, HCP, and BCC.
Wait, does it curve back like that?
Yeah, the lambda line is weird. This curve, like, is that what you're talking about?
Mm-hmm.
Yeah. So it kind of behaves like water in that sense, but this is 2 liquid phases. So what is the 2 liquid phases too? That's a little weird. So what about a liquid could be different? I mean, how would you have 2 phases of liquid?
Densities.
Yeah, different densities and different surface tensions and different viscosities and so on. In fact, this superfluid, liquid helium-2 superfluid, a superfluid is a liquid. It has a meniscus, but it doesn't have any surface tension. So there's no energetic penalty for forming new surface. Now this is bizarre because you're used to water, which has a high surface tension, and other liquids too, which have moderately high surface tension. So when you pour a liquid in a cup, it may wet the glass like water does, but then eventually it stops rising because of its weight and because of the energetic penalty for making surface. So if I've got a molecule or an atom in the middle of the bulk, liquid, and I want to move it to the surface, what do I have to do? To create surface, I've got to break all of the intermolecular attractions on the top, because this has to become on the surface, so I'm going to scrape all of that away. And that's energetically costly, not for helium superfluid. So it doesn't cost any energy to make surface. So if you poured helium superfluid in a cup and it wet that cup, it would wet all the way up the sides and all the way down the outside. Because it doesn't cost any energy for it to make surface. And so it would just keep making surface. And if it was getting energetic benefit from wetting the cup, that would certainly overcome the non-energetic loss of making new surface. And so it would just wet the cup. And if it wet the countertop, it would spread out on the countertop. So you pour a superfluid in your mug, and if it wets everything, it goes and wets everything. It spreads out until it's monolayer on the surface. Yeah. And so that's totally bizarre.
That's crazy.
You can find videos and pictures of helium superfluid in the middle of a container, and there's a meniscus in the middle, and it's wet everything, even the top. So it's like it's in a container, it's wet all the surfaces, and the meniscus is in the middle.
That's pretty crazy.
Yeah, that's really weird. I know. So that's some trivia about the superfluid. Okay, let's go back to the HCP BCC.
I'm trying to understand.
Yeah. Okay. It's solid phases. What can you do with helium? I mean, really, it's marbles in a jar, right? And so there's different ways you can pack marbles in a jar. You can have a hexagonal close pack, right? So you have them all in a hexagonal pattern, and then you just alternate the layers A, B, A, B, A, B. And if you look at that diagonally, that would be a face-centered cubic structure or hexagonal close pack. Those are synonymous. Okay, so HCP is hexagonal close pack. Now, if you put the B layer, if you have some holes in the B layer, the A layer is hexagonally close packed, but then the B layer has some holes, then you get a body-centered cubic. So BC, C would be body-centered cubic, and HCP would be hexagonal close pack. Hexagonal close pack is the most dense, and that's why it's the higher pressure one. And so you can Google those structures and see them. Now, let's put these two phase diagrams together. This is what Jared's mind just blew up with a little bit earlier. It's because he saw what was going on. We had the PT diagram, and we had the PV diagram, and we got this in the middle. Isn't that great? I love this.
Hard to look at.
Yeah, it's so cool. And since it's hard to look at, I 3D printed one. So you can pass it around. Yeah, and this is for water, okay? And I've got a black line on here that was the best I could do for an isobar. So that's 1 atmosphere, pretend. Okay, and you go across and you see solid, then it melts, then it boils, and then you got a hot gas here, so we can pass that around. I'm going to go quickly so that everybody gets to see it before class is over. So again, I should be able to drop you in here anywhere, and you tell me where you are. Am I a gas? Am I a liquid? Am I in equilibrium, gas, liquid? These little red lines through here, you should be able to tell me every path. You start at G, you're gas. I start cooling you down. At H, you start to condense. Okay? And so here I'm at H. I'm condensing. Where's my pen? Okay. I'm condensing. Then I'm all liquid. And I'm squeezing. I'm still at the same temperature, but I'm changing the volume. So it's getting more and more dense. Now I've got a solid forming. Now all the solids form, and now I'm squeezing on the solid. Okay? So you should be able to walk through this phase diagram on any one of those paths. And to connect it to the previous set of notes, there's the Carnot cycle. What? Wow. So now you can see the isotherms and the adiabats, and how the adiabats are steeper because they're not staying on that temperature line. They're just rolling downhill. And I've drawn that Carnot cycle on the little phase diagram. But see, we were over here at PV looking at it that way. Yeah. Yeah. All right. And so that's A, B, C, and D, the 4 legs of the Carnot cycle.
Oh, it's over there.
Yeah. Oh, you didn't find there it is.
I didn't realize that it's drawn.
Yeah.
I was like,
It's the busiest plot I have in the whole semester. Okay, so this is the top of the hill, the busiest phase diagram. But when I saw this in that book, I was like, I love this book. But then it just had some other things. I like Atkins better in general, so we went back to Atkins. And so you have the isotherms and adiabats identified. And so then this rest of the stuff, again, is just kind of definitions of normal boiling point, standard boiling point. They're different. So that's kind of weird. Standard boiling point for water at 1 bar is 99.6 degrees C. So that's why nobody talks about the standard boiling point, because you would totally screw that up. You know, the normal boiling point is 100 C, and that's 1 atmosphere. So this whole bar thing, we can just get rid of, and I'd be happy. Yeah. Supercritical fluid, the density of the gas is tiny, the density of the liquid is big, and as you reach that supercritical regime, it's more close to the density of a liquid, but it's gas-like in that it fills the whole container. So again, just a picture of what's going on with the supercritical fluid. It's not that the critical fluid is irritating to be around, right? It's just that it's above the that's today's joke. Yeah. All right. So I'll see you next time. The supplemental material is kind of just FYI.